Okay, let's talk about the material from lecture 25. This is the lecture on correlation. As always, this video is not a substitute for reading the book and notes. You ought to do that, because there may be things in there that you will need that are not discussed in this video. Alright, so you remember last time we were talking about regression, right? Drawing a line through some dots using a linear model to represent some bivariate data. And throughout that discussion, we said that we were just simply going to assume that using a linear model was okay and talk about when it was or was not okay later. Well, this is the time we want to do that. Right? We want some sort of a measure that we can compute from the data that will tell us whether it's reasonable to use a linear model. What we're going to use for that is something called the correlation coefficient. Correlation coefficient, which is always symbolized with R. Sometimes you'll see a capital R, but usually a lowercase r. And what R does is it tells you how close your data points are to being on a straight line. Right? When R is equal to -1, the points lie on a line with negative slope, right? Sloping down from left to right. When R equal 1, they lie on a line with positive slope. That is a line that slopes up from left to right. We will actually compute R with a calculator, and I'll do a little example of that later. Right? But we want to get an idea of what it means. So first we're going to show pictures and then talk more about that, what it means. Okay, so you know when R is -1, the points are just going to line right up on a straight line. Oops, that's when R is 1. That's a line with positive slope. It slopes up from left to right. When R is -1, right, then the points are going to line up along a line with negative slope. R is not the slope, by the way. This slope doesn't have to be 1, and this slope doesn't have to be -1. But R does have the same sign as the slope. Okay, here are some other examples. Here is R equals -0.8, -0.8, and you can see these dots are reasonably close to some line. They're pretty messy, but if you use the line as a predictor, you really wouldn't be that far off in most cases. Right? Remember, if you had an X value here, and you went up to the line and found the Y value, right? This point right here, this point would not be a terrible predictor of what you would expect the Y value to really be. So R equal -0.8, that's a pretty strong correlation. R equal -0.6, there's still a pretty clear linear trend in that data. Of course, the dots are farther away from the line, which means that the linear model would be a worse predictor, but it's still useful in that case. Here we're getting into the range where you just got to be careful. This has R equal -0.4, which means there is a linear trend. We probably can see it by eye, but a lot of the points are pretty far away from the trend line. Right? The trend line would be probably really a poor predictor. It's good to know that there is a linear trend in which way it goes, right? But using the line as a predictor would be probably a bad idea in most cases. When R is equal to -0.2, it's hard to see a linear trend in the data at all. It's there, right? It's a measured trend, it's -0.2, so the data is kind of sloping down slightly along a line. But you wouldn't want to use it as a predictor at all. When R is 0, there is no line that tracks that data. Or, if you want to say it another way, any line you draw through this data will be just about as bad a predictor of it as any other line. The rest of these pictures are pretty much the same thing, only for positive slopes. Right? This is r equal 0.2. It's a lot like r equal negative 0.2, except that it tracks, there's a slight positive linear trend in there. And the same with these others. When r is 0.4, there's a discernible linear trend, but it's not strong. When r equal 0.6, now we're beginning to get somewhere. You actually would consider using this line as a predictor of where the y value would be given an x value. And of course, when r is 0.8, it's a pretty good predictor already. Okay, with that in mind, let me write down some stuff about the properties of r. Properties of r. Right, first of all, as you already know, r is always between 1 and minus 1, inclusive. R can be equal to minus 1, r can be equal to 1. But it doesn't usually happen because that means that the points lie on a straight line. Now there are two parts to interpreting a value of r. Right? The size of r, the absolute value of r, determines how strong the correlation is, and the sign of r, whether it's positive or negative, determines the direction of the correlation. We're going to say that when the size of r, when the absolute value of r is less than or equal to 0.3, that this is called a very weak correlation. You probably don't want to use any sort of linear model when r is that small. It's possible. The only time you would do it is if you had a lot of data points, and when you made the scatter plot, you could actually see that there must be a linear trend in it. Okay, if r is, let's see, if r is in absolute value, greater than, strictly, if r is greater than 0.3 but less than or equal to 0.5, we'll say that that is weak correlation. I don't know why I keep putting e's on the end of that. Right? When data is larger than 0.5, when r is larger than 0.5 but less than or equal to 0.7, right, we'll say that that is moderate correlation, moderately strong. And then if r, absolute value of r, is greater than 0.7, we'll say that that's strong correlation. Not everyone would define these the same way, but most people would agree that if absolute value of r is less than or equal to 0.5, well, let's just say hesitate to use a linear model. One might be useful, just as we saw when r is 0.4, there is a linear trend, and it's good to know it's there, but the prediction value of the trend line is very weak. Okay, so the size of r, the absolute value of r, tells you how strong the correlation is. The other thing about interpreting r is the direction of the correlation, and you've already heard about that, right? When r is less than 0, this is negative correlation. That is to say, the line that tracks the trend, the trend line, has a negative slope. It slopes downward from left to right. And when r is greater than 0, you get a positive correlation. That line slopes upward. When r equals 0, there isn't any correlation at all, so there is no trend line. Okay. Let's see here. Let me say a couple things. I'll do a couple examples in a minute, but I need to say a little bit more about this stuff. First of all, r near 0 does not mean that there's no relationship between x and y. It simply means that there is, whoops, you can't see that. Sorry about that. Right? No relationship between x and y. It means that there's no linear relationship. There might be some formula you could use to explain or predict y from x, but it won't be a linear formula. Right? It won't be a y equal ax plus b. So here, for example, here's some data, and I'll draw in the data points. There are the data points. Right? This data lies exactly on the curve y equal 1 minus x squared. So if I knew a value of x, I could easily determine the value of y. Right? So the relationship is perfectly clear. However, for this data, r will be 0, right? Because there's no line that tracks that data. Okay, that's just something to be aware of. R near 0 means that there's no linear correlation. Okay, we've got one more quantity in this section, and that is r squared. R squared is called, I have to say it, the coefficient of determination. A horrible name for something which I generally will try not to use. R squared, what R squared tells you, it's the percentage, if you like, the fraction of the variation in y that is explained by x. Well, r squared is just the square of r, and r is between minus 1 and 1, so r squared is always between 0 and 1. Right? R squared is always between 0 and 1. When r squared is near 0, right, that means a small amount of variation in y is explained by our model. Right? We say by x, but it's really by the model. And that says that the model isn't very good. Right? If you think about it in terms of a predictor, that means there's an awful lot of variation left over to explain. You've only explained a little of it. When r squared is near 1, right, then a large amount of the variation is explained. A large amount of the variation is explained, and so the model is pretty good. Right? Okay. Let's do a couple examples here. Here's the first one. Here's the first example. A study of the correlation between high school GPA and first-year college GPA for more than 63,000 students found R equal 0.39 at the 0.05 significance level. We won't study significance in relation to correlation in this course, so that's really irrelevant to us, the significance level. However, R is 0.39. How much of the variation in first-year college GPA is explained by high school GPA? Well, we have R is 0.39, so R squared is just 0.39 squared, which is about 0.15. You can take out your calculator and verify that. Right? And so we say that about 15% of college GPA is explained by high school GPA. Notice that I did not say 15% of the variation in college GPA is explained by high school GPA. That is the true situation. Right? But the fact is that people mostly don't say it that way. They just say about 15% of college GPA is explained by high school GPA. Okay, let's do one where we have to actually compute the correlation coefficient and the coefficient of determination. We have this table. We've seen it before. It has the ages and salaries of 10 secretaries at the XYZ Corporation. Determine the correlation coefficient. About what percentage of the variation in salary is determined by age. So we got two things to do, correlation coefficient and then answer that question. So how do you get the correlation coefficient out of your calculator? Well, let's see, would it help if I turn this off? No. How about if I turn it down? I don't know. Anyway, here's what you do. You take this data and whatever your, let's see, about what percentage of the variation in salary is explained by age. So we're going to want salary to be explained by age. So age is going to be our X and salary is going to be our Y. Okay? So we're going to put the age numbers in L1 and the salary numbers in L2. If I go to Stat Edit, you can see I've already done that. So I don't have to do it. Okay. Now, to get the numbers we need, the R and R squared, we just go to Stat, and then over to Calc, and down to number 4 there, linreg AX plus B, and press Enter. Oops, and press Enter again. Right? And there you can see, as before, we have the regression line, we have A and B, the coefficients of the regression line, and then we also have R and R squared. Well, your calculator may not show R and R squared right away because for some weird reason the default setting in these calculators is that they don't show that. If they don't show that, go to the book or to the notes, to this section, and you'll find instructions in a little box. Let me just go over them here and I'll come back to this. Right? Here's how you do it. You would go to, you want to go to the catalog function, which is above 0. So you hit second, 0. And this is a catalog of everything the calculator can do. You want to get down to the D's, and the quickest way to do that is to push the x to the -1 key there. That gets you down to the D's. And now you have to arrow down, and you want to keep arrowing down till you get to diagnostic on. Make sure you can see that, diagnostic on. You press enter, and then enter again. And then it will show R and R squared when you do that stat calc 4 thing. So let's do that. Stat, go over to calc, and hit 4 to go to the 4th menu choice. And Bob's our uncle. What do we have there? We have R is about 0.53. Close enough. R squared is about, what is it? 0.28. Okay. So actually computing this stuff is really the easy part. Okay, about what percentage of the variation in salary is explained by age? We use R squared, interpreted as a percentage, to answer that question. So R squared is about 0.28, so that says that about 28% of salary is explained by age. At least as far as we can tell from this data. Okay, I got to talk about one more thing, and that is the relationship between causation and correlation. You can have a strong correlation between two variables without having any causal relationship. Here's a picture of such a thing, but particularly absurd example. Right? It is true, by the way, that if one thing causes another, then there will be correlation. Right? For example, when your foot size changes, your shoe size changes. Right? That's going to happen. So if you go around and measure people's foot size, and you go around and measure those same, and take a look at the average shoe size of the shoes in their closets, you're going to see a strong correlation between those, because foot size really does cause shoe size. It doesn't work the other way around, and the correlation would still be there. Buying bigger shoes won't give you bigger feet, but you'd still see exactly the same correlation coefficient. But at least there you have causation in one direction. Many times you don't have causation in either direction. And here, this is from a website called tylervegan.com that collects these spurious correlations, as they're called. Correlations, strong correlations of data that have nothing to do with one another. It may be hard to see on that screen, but one of these curves tracks the divorce rate in Maine between 2000 and 2009, and the other one tracks the per capita consumption of margarine in the whole country over that same period. Right? And you can see they almost exactly match, and the correlation coefficient is amazingly high, over 0.99. And yet they have nothing to do with one another. Right? For example, would an increase in the divorce rate in Maine cause people to eat more margarine all over the country? Or the other way around? Of course not. Right? It's absurd to think so. And yet the correlation is extremely high. And what has happened here is what happens a lot, is that two quantities which are completely unrelated just happened to change in about the same way over about the same period. And so when you just look at the data, they're highly correlated, but there's no causation in either direction. You can find examples of people assuming that correlation implies causation in almost every newspaper, almost every day. It's a very, very common mistake. Be cautious. Okay, that's about it.